Well, my name is Alex Vergara again, and today I'm going to be presenting my paper entitled Thermal-Assisted Transient Response Analysis to reduce the response times of microplate gas sensors. Okay, so we all know that for many years scientists have been interested in reproducing our biological senses. Chemical sensing is not the exception, and as demonstrated by the many different applications in which, in particular, gas phase detection by chemo-resistive transduction have been implemented in many different applications areas, ranging from medical applications in which the chemical sensor devices are used as non-invasive detectors of many different diseases, as well as, I don't know, military environmental applications, industrial applications, or space-based applications. As efficient as all these devices have proved to be in many different applications, they still have many problems, which are those related to selectivity, sensitivity, stability, and especially they are very slow in the response. So many different works in the intersection of biology, signal processing, and material science and nanotechnology have been working together in attempts to counteract all these problems. However, despite promising results in all these areas, there's still one unaddressed point, which is that of speed. Chemical sensors or any kind of sensors are very slow in the response. So with that motivation in mind, the question that we are trying to address here is how can we possibly accelerate the response kinetics of this sensor so that we can achieve or we can complete chemical tasks more rapidly, and still reliably. So with that question, we're trying to address that question here by implementing an combined optimization strategy consisting of rapid temperature modulations along with signal processing formalisms to answer for the first time whether and how we can accelerate that sensor-analyte response time without compromising the performance. In the following slides, I'm going to be walking you through the approach that we are implementing here, as long as presenting and discussing some of the results that I have obtained in this work. Finally, some concluding remarks that I would like to emphasize at the end of this presentation. So we all know that metal-oxide sensors are by far the most widely sensing technology that have been studied all over the world. Not only because this is pretty much the only sensing technology that has been fully commercialized by Figaro for over 20 years, but also because this sensing technology presents a series of advantages with respect to the other sensing modalities, such as they are easy to use, they have low cost, they have a relatively high sensitivity to many different organic compounds, and more especially, they are robust. There are some works that demonstrate that metal oxide sensors have been working for over 4 years without any major problem. The basic principle of operating principle of this metal oxide sensor is rather simple, and basically consists on the exchange of oxygen electrons between the sensing film and the gas being detected, that in turn will depict a exponential like transient response that will exponentially increase or decrease depending on whether we are measuring resistance or conductivity up to it reaches a quasi-equilibrium state or steady state. That the shape of that response is going to be specific to the analyte and concentration that we are measuring, and will depend on the sensing material, the operating conditions in the sensing device, and more importantly on the most natural operating parameter, which is temperature. With that knowledge in mind, then our previous question before will change to the following 2 points. First, can we utilize temperature as an operating parameter to accelerate the response by implementing rapid temperature modulations? And if that is the case, what is the role of the frequency utilized to modulate or in modulating the working temperature of the sensor? So to answer that question, let's go and answer the first question first. So let's consider a microhotplate gas sensor with a sensing field of, let's say, indium oxide, in the presence of 4 different analytes, each those at many different concentration ranges. What's happening? And while we are exciting the operating temperature of the sensor by a program like the one I'm showing here, which is simple temperature pulses at a relatively high frequency. The idea then is to apply this to the heating element of the sensor and evaluate the effect in accelerating the response of the sensor by looking at what we call temperature enhanced transient response of the sensor in response to the chemical analyte. So, in answer to the previous question before, the answer is a resonant yes, in which we are basically passing from the typical 1 minute over response in reaction to a chemical compound to just as little as 10 seconds in and we are generating, of course, that accelerated temperature enhanced transient response. This answered the first part of the question, but the second question of what's the role of the frequency still remains open. So to answer that second question, then we are going to start analyzing, we are going to start applying or heating the sensor, exciting the sensor with the same temperature program, but at different systematically varied temperature modulation frequencies. And then we're going to generate for each one of these frequencies our temperature enhanced transient responses and analyze them as a function of the time it would take for the sensor to reach that quasi-equilibrium, which obeys pretty much this equation here, which tells us exactly the point in which the sensor response is reaching that quasi-equilibrium point. So in this graph here, we observe that for many different frequencies utilized, we are definitely getting a better or a faster response of the sensor, and a faster response in the sensor relative to that isothermal version of the sensor response. More importantly, we can identify which frequency will give us the faster response. That by itself represents an optimization problem approach in which the objective function is to determine which frequency will give us the fastest sensor response. However, that's just a very small portion of the whole picture. Why? Because we also want to determine what is the role of that frequency in terms of performance. So to do that, we are going to include the second term in our optimization approach, and then we are going to design a combined optimization problem, which basically consists in maximize the discriminative information coming out from the sensor while minimizing the response time of the sensor. That's pretty much given by this equation here, which eventually will give us the optimal trade-off between minimum sensor-analyte response time and maximum performance. So how do we determine D, meaning the performance? Well, one of the important advantages of this methodology is that it's not directly convoluted to any particular machine learning or pattern recognition technique to determine that performance, or information measure technique. So in this project, we are introducing a relatively new methodology based on information theoretic formalisms called the mutual information. That mutual information basically defines or gives us the information that one random variable, let's say our measurements, contains about another random variable, that is the chemical task that we want to address, whether it's a gas discrimination problem or a gas quantification problem. So from our 3,000 plus measurements of each one of the gases, each one of the concentrations, 11 different frequencies, we are going to extract a bank of features that will represent each and every one of these measurements that we are going to organize according to the task that we want to address. In particular, we are utilizing a family of features coming from or borrowed from the field of econometrics, which will, given our transitory response, like the one here, will express all the information contained in that response by different peaks, the different peaks that I'm showing here. We are going to concatenate them together and give it to our machine learning algorithm, the mutual information. That will give us the information, the amount of information that the sensor working at each temperature will have. This result again confirms our hypothesis that by working with rapid temperature modulations, we can accelerate the response, but most importantly, that we have different effects utilizing different temperature modulation frequencies. Since that algorithm and our algorithm is not committed to any pattern recognition technique, if we utilize any generic classifier, that information given by the mutual information should correlate straightforwardly with the information given by the classifier. And then, if we provide that information to our combined algorithm, then we are going to be able to determine from all the different frequencies which frequency is the one that will give us the optimal trade-off between minimum sensor response and maximum performance, which for this particular experiment in discriminating the 4 different analytes regardless of the concentration happen to be frequency of 30 milliseconds, in which we obtain basically the maximum performance and the minimum response time. That numerically it's summarized pretty much in this table here, in which here we have the 4 different analytes. In the main column we have the different analytes that we are obtaining in performance, and obtaining 98% in only 9 seconds. That definitely compares favorable with respect to the isothermal version that we showed before. Working with that is definitely shows definitely great advantage with respect to this approach. However, for certain applications, working on 10 seconds or 9 seconds is still too much. So to avoid that problem, we decided to go even further and analyze different portions of the transient response, here highlighted in red, of our temperature accelerated transient response, and repeat pretty much the previous approach that I just explained. That is again graphically summarized here, in which on the y-axis we have the different frequencies that we are analyzing. Here we have the different time windows of that temperature enhanced transient response that we are analyzing, and the performance is shown here by the intensity and the color on each one of these plots. So intuitively, what we want to achieve is, what we are looking for here are those dark points, and that should happen as soon as possible. This table here simply summarizes some of those peaks in which we were able to even quantify, for example, methanol at 92% in as little as 3 seconds. There are some standing questions, of course, as of whether we can utilize these sensors on real application scenarios, as well as how long can the sensor operate under this temperature excitation program in long stand applications. That's part of our ongoing research that we are currently investigating, and we are obtaining already results on that. So as a final and concluding remark, in addition to what I just presented here, I would like to emphasize one thing. Here, for the first time, I'm utilizing temperature modulation not to increase the performance of the sensor, as has been utilized before, but instead I'm using temperature modulation to accelerate the response of the sensor, while trusting in the natural capabilities of the sensor to achieve those chemical tasks. Finally, I would like to thank the National Research Council for funding my research, as well as Steve Semancik and Kurt Benkstein present here for hosting me at NIST and contributing with me in my research. Thank you very much.